All right, today's lecture is going to be a review of electron configurations. Now, for some of you, this might be pretty simple, and you remember a lot of the tricks and tips of how to do this. So you might be able to go through this really quickly. Others of you might need to, again, listen to the full in-depth lecture to kind of review these concepts. Just because you kind of think you have it, I would still strongly recommend. I have a homework on page, I believe it's on page 5 of this packet. I also uploaded it because it's kind of, it's been turned in this packet, but I've uploaded a Microsoft Word format of it where it's more easily that you can do the homework problems, or you can just print off that single page and do the problems at home if you have access to a printer as well. But really do the homework, get practice doing it, because usually they don't ask for the full electron configuration. They might ask for just the valence electron configuration, so doing some of these practice problems is really essential. Now, electron configurations is talking about, if we look back at the Bohr model of the atom, we've got that nucleus, positive nucleus with a certain number of protons and neutrons. And we have the energy levels. Electron configurations is looking at how many electrons can we place in each of these orbitals, and then we continue to move out and fill. When we fill these orbitals, okay, now Bohr model, these are rings, but we know today that they're actually called orbitals. These electrons, they fill typically in an order where the lowest energy orbital is filled first, and then they work their way out. That down below is the rules that we follow down here at the very bottom, how we do these orbital notations. But each ring is an energy level. On the periodic table, again, the top row, think of this as being that first ring closest to the nucleus. If we are going to put electrons in orbitals, we typically do first ring, then second ring, we work our way out. As electrons move out to higher and higher rings, they have higher energy associated with them, okay? Because of this Coulombic attraction, the further you get away from the nucleus. And so each of these on the periodic table, each of these rows or periods on the periodic table is associated with a specific ring around the nucleus in the Bohr model of the atom, okay? If you remember, there are 4 blocks to the periodic table: S, D, P, and F. That's because if we are putting electrons in that location of the periodic table, we are putting them in that specific shape of an orbital: a d orbital, a p orbital, an f orbital, so on and so forth. And again, to review what those orbitals look like, an s orbital is a spherical orbital. A p orbital is a dumbbell orbital. A d orbital is a double dumbbell orbital. And an f orbital is a complex orbital. These are the different shapes of orbitals that we put electrons in. And then we fill electrons in each of these. And we, again, are guided by these key fundamental rules here at the bottom of the page to be able to do these configurations. So, for the most part in this lecture, we're just going to focus on how do we remember the order at which we put the electrons in to do an electron configuration question if that is asked on this year's national exam. Okay? One trick to remember that is called the diagonal trick. On the first floor, I think most of you can remember that all that we have is the 1s orbital. Once we fill the 1s orbital, the first ring of the nucleus, the first ring of the nucleus in the Bohr model only takes up to 2 electrons. After it is full, we move out to the next ring, or the second energy level, which is given by the 2s. The number out in front is what ring, what energy level we are around the nucleus. The next letter tells us what shape of the orbital we're putting electrons in. So a 1s tells me I'm on the first floor, the first ring, and it looks like a sphere. If I'm doing a 2p orbital, we're on the second ring of the nucleus, and it's shaped as a p orbital, as we see above in the shapes. Okay? So one way to remember this is each floor we go up, we gain another letter. On the second floor, there's 2s and 2p. On the third floor, there's 3s, 3p, 3d. On the fourth floor, 4s, 4p, 4d, 4f. The first time we see an f orbital is on the 4th floor, or the 4th period on the periodic table. That's the first time we see an f orbital, is on the 4th floor. After the 4th floor, 5th floor, 6th floor, 7th floor, all of them repeat. We no longer have any other shape except up to F. So if we put the diagonal trick down on a piece of paper like this might be something you have out when you take the national exam, that you can easily look at and go through the sequence. But the sequence to put orbitals is we use a diagonal line and we fill top down. So the first orbital we fill is 1s. After that, we do the next diagonal line and we cover 2s. Then the next diagonal line, we hit 2p, 3s. And then next diagonal line, 3p, 4s. Then we fill 3d, 4p, 5s. So after 4p is 5s. And then we go to the next line, which would be 4d, 4p, 6s, 4f, 5d, 6p, 7s, and so on and so forth. So if we use these diagonal lines, we can use the diagonal trick to give us the exact sequence that we put electrons in. One other thing to note is electrons, as you can see here in step 3, an s orbital takes up to a maximum of 2 electrons. Once we have 2 electrons in this orbital, it is full. We then have to go to the next orbital as dictated by the diagonal trick. If it's a p can take up to 6. Why not 2? That's because p's, if you remember, come in 3 variations. Each one has a lobe that is directed along one of the 3 axial planes. Each of these orbitals takes 2 electrons to fill it. That's why with the p it takes up to 6 electrons. To fill all 3 of them, it takes 2 in each for a total of 6. D's, they come in 5s, F's come in 7s, and that's why the D's will take up to a maximum of 10, F will take up to a maximum of 14. S, there's only one shape of the orbital. A sphere, no matter how you move it or turn it in space, always looks identically the same. So an s orbital will only take up 2 electrons to fill it. All right, so let's go ahead and do some practice doing this. So again, the order I've given you up at the top, but that's something you might want to just practice every day. Just quickly write down the order or have it down in front of you to do these homework problems. All right, so the first step is to figure out, as we can see up here, is to figure out how many electrons the atom has. My lower students, this is a struggle for some people, and this is the key thing to review. How many electrons these particles have. So chlorine, element symbol Cl, look up on the periodic table, and chlorine has got a 17 on top and a 35.45 on the bottom. Remember, the top number is the atomic number. What does that tell you? The atomic number tells you the number of protons in the nucleus. But that is also equal to the number of electrons if it is an atom. An atom is electrically neutral, so the number of protons is equal to the number of electrons because the atom is electrically neutral. The bottom number, again, remember, is the atomic mass, which is the average mass of all the isotopes of naturally occurring chlorine. Chlorine has 2 naturally occurring isotopes, a mass of 35 and a mass of 37. So the atomic mass of 35.45 will always be in between the lowest isotope weight and the highest isotope weight. But again, weight is not important in doing electron configuration questions. We want to look at the atomic number, and that tells us how many electrons. So chlorine has got 17 electrons. So now to write the electron configuration, we just simply go ahead and fill. So the first orbital we fill is 1s, which takes up to 2 electrons. So we say 1s2. So the first 2 electrons go in the first ring. After it is full, it moves to the second ring. And if I look at the top, the next orbital to fill is the 2s. It is also an s orbital. It will take up to 2 electrons. So the second set of, or the next electrons, 3 and 4, go into the 2s orbital. When it is full, it moves out to the 2p's. Okay, the 2p takes up to 6. Okay, so 6 more electrons are placed in the 2p to fill it. Now, if you add up the superscripts, 2 plus 2 plus 6, that's 10 electrons. So the first 10 electrons go in these orbitals. Now, the second floor is full, so we now move up to the third floor. 3s2 now gets me to 12 electrons. 3p, now the p will take up to a maximum of 6, but I don't need 6 because chlorine I only got 5 more to go. So right there is the electron configuration of chlorine. So if on the national exam this year they said, what is electron configuration of chlorine? You would say 1s2, 2s2, 2p6, 3s2, 3p5. if we add up all of the superscripts, that should add up to the number of electrons. That's how you can check to make sure your number is right. All right, iron, Fe, has 26 electrons. So if you want to pause the lecture now and try to do it on your own, and then check your answer, please do. 1s2, 2s2, 2p6, 3s2, 3p6. That gets us up to 18 electrons. So whenever we do 18 electrons, we get up to 3p6. Now here becomes the issue. Students want to put down 3d, but if you remember back from honors, we put electrons into 4s before the 3d. So the next 2 electrons go into the 4s, and then the next set of electrons go into the 3d. Now 4s2 gets us up to 20 electrons. We need 6 more. The d takes up to 10 electrons, so 6 is perfect. We don't have it full, but that gets us to the last electron. The 26th electron is 3d6. So again, the 4s fills before the 3d. Why? Energy. The 4s orbital is a little less energetic than the 3d because of the complexity of the 3d orbital, and therefore we fill the 4s orbital before the 3d. Now once the 3d orbital is full, then we continue filling the 4th floor. So since the 4s has already been filled, we then go to 4p, as we again can see at the top where we see the order of filling. All right, let's go with the bigger one. Tellurium, Te, has got 52 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. D takes up to 10 electrons. After 3d, then we go back to 4p, 4p6. Now in honors chemistry, I said the maximum you had to worry about is 4p6. That got it up to krypton. In AP chemistry, you could do a configuration of any element. So you've got to be able to do the diagonal trick all the way out as far as you can get. Okay, so after 4p, if we follow the diagonal trick, after 4p, we fill the 5s. Again, it's an S, takes up 2 electrons. That gets us up to 38 electrons. After 5s comes 4d, which takes up to 10 electrons. So now we are at 38, that's 48. We got to get to 52. After 4d comes 5p, and we only need 4 more left. A p takes up to 6. 4 means we're not full, but we have up to 52 electrons. So 5p4 would be tellurium. Okay. Now, one other thing, if you remember about orbitals, the very last orbital is a critical orbital. So tellurium being 5p4, that tells us a lot of information. The 5 tells me on the periodic table that I'm on the 5th floor. And the 5th floor starts with the atomic symbol Rb, rubidium. Tellurium should be in the period containing Rb. And it is, because tellurium is way over here. It's on the 5th floor where rubidium starts that floor. The P tells us we should be in the P block, or the furthest right block in the periodic table. The 4 tells us in the P block. And the P block has got 6 columns with it. Any element in the first block, first column, is P1, P2, P3, P4, P5, P6. So P4 tells me I'm in the 4th row of the P block. And if we notice, if I take the 5th floor and the P4 and I drop it down where those 2 lines vertically meet, we end up meeting right at tellurium. So that 5p4 tells us the exact location. The very last orbital in the configuration tells us the exact location of that element, and it should match where it is found in the periodic table. Something to consider. The abbreviated electron configuration we'll talk about here in a second on the next page. Okay, so how many electrons fill an orbital? If it's just one specific orbital, 2 electrons. 2 electrons can only be filled maximum. Okay, that's the most it can fill. Now, if you remember the rules, if you have 2 electrons in an orbital, Pauli exclusion principle, one of the key principles to doing this stuff, says that if there's two electrons in the same orbital, they must be spinning in opposite directions. Okay? Aufbau's principle says electrons go in the lowest energy orbital available. Once we fill the 1s, we fill the 2s. When it's full, we go to the 2p, so on and so forth. Okay? The last one is called Hund's rule. Hund's rule states that if we have orbitals of equal energy, 2px, 2py, 2pz, when we fill p orbitals, if they are equal energy, if they all share the common first number and first letter, 2p, 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 when we fill them, if you remember back from honors chemistry, arrows are electrons. We must put one electron in each orbital before we double up. So when we do Hund's rule with electron configurations, if we have to do an orbital notation like this, we always put one electron in each before we double up. Now, while I state that, on the national exam, I highly doubt you're going to do an orbital notation because it's gone down to 45 minutes, very limited nature. If you're asked to do electron configuration, I am almost guaranteed you'll have to do electron configuration, 1s2, 2s2. So I wouldn't be too worried about Hund's rule for this application. Just know the order and know how many electrons to put into each. And that's maybe even something you have across the top of your page when you take the national exam. Have that order out for you already, and then you can easily do that problem very quickly and efficiently. Okay? I'm not telling you really to cheat, but it's something that you can obviously have at your availability that you might find very useful. Okay? All right, how many electrons fill the 3D sublevel? The 3D sublevel is all the electrons of the 3D. How many 3D orbitals are there? D's, all D orbitals come in a pack of 5. There are 5 of them. Each orbital takes 2 electrons. So to fill the 3D sublevel, to fill the entire set of all the 3D orbitals, it takes up to 10 electrons, which should make sense because I said a D takes up to a maximum of 10. If it's an F, there's 7 of them. When we have a 4F, there's 7 4F orbitals. Each one takes 2. That's why we have a maximum of 14 electrons. Okay? What's the only difference between 2 electrons in the same orbital? Their spin. If I've got 2 electrons in the 2s orbital, the only difference is one electron is spinning one way, the other electron is spinning the other way. And the reason they do this is to minimize their electron repulsion, and therefore they're able to stay in the same orbital even though they have the same charge and they want to repel against each other. There are 2 exceptions that you should know going to the national exam for electron configurations, and that's copper and chromium. If you do the complete configuration of chromium, I'm going to do the last 2, your prediction for chromium would be 4s2, 3d4. But this is not the correct configuration. What actually happens, if you remember back from honors, one of the electrons from the 4s jumps into the 3d, and so the very 2 last orbitals, to do the full electron configuration of chromium, you can look it up if you want, but the last 2 is going to be 4s1, 3d5. One of the electrons goes from the 4s and jumps into 3d. Why? This is what you would expect to be happening. 4s2, 3d4. But you'll notice that there's an open 3d orbital that's vacant. So what happens is the atom pulls one of the electrons from the 4s and puts into 3d, creating 4s1, 3d5. Why? Because if that electron goes into that vacant orbital, which we're already filling anyway, even though the 3d orbital is a little bit higher in energy, we're able to minimize the electron repulsion of the 2 electrons in the 4s, and this configuration is got less energy associated with it because of that minimizing electron repulsion, and therefore it is the preferred configuration. So any element in the chromium family is going to put one of the electrons from the 4s and throw it into the 3d. The same thing happens with copper. Copper you'd expect to be 4s2, 3d9, but again what happens is one of the electrons from the s jumps into the d to totally fill it, and the preferred configuration is 4s1, 3d10. These are the only 2 violations of the rules of how we fill electrons that I talked about in honors. It'd be the only 2 that I would expect that you would have to maybe know for the national exam. Okay, so that's how I do electron configuration. Now we're going to go to the next page where so far we've been doing atom configurations. What happens if they do ion configurations, which is usually more likely on the national exam. So let's go ahead and do that one. All right, to do an ion configuration, what you have to identify is it is not an atom. So if we look at nitrogen, nitrogen has got 7 electrons. That is when it also, because the atomic number of nitrogen is 7, whenever it's an atom, electrically neutral, it has 7 negatives and 7 positives. Okay, it's an atom, it's a neutral particle. But if you're asked to do an ion, now you have to do the configuration where the number of electrons doesn't match the protons. In the nitride ion, how has it become a -3 charge? Can it lose protons? No, we never can touch the proton number. If we change the proton number, we are no longer talking about nitrogen. All nitrogens always have 7 protons. We can't change that. So how do we form a negative ion? We gain electrons. So to be a -3 charge, instead of having now 7 electrons, we have gained 3 more, and so we have 10 electrons. So what we're really doing is we're doing the electron configuration not of normal nitrogen, but of the element that has 10 electrons. We are really doing the electron configuration for neon. So for anything that's got a negative charge, take the number of electrons it normally has as an atom and then add the amount of electrons by the negative charge. If it's -1, you add 1 electron. If it's -2, you add 2 electrons. So now we want to look at the electron configuration of 10 electrons. 1s2, 2s2, 2p6. So the nitride ion has got the same configuration as neon. What do we want? Neon? Neon is a noble gas. Why do atoms lose or gain electrons to become a noble gas configuration? Because that's the most stable configuration. All of the electrons in the floors that electrons are located in, especially the outside row, which is the valence row, is completely filled, and therefore it is the most stable configuration, and therefore it's the least energetic configuration. That is the preferred configuration of the ion. What do we do when it's a positive ion? Magnesium normally has 12 electrons, but if it's +2, it has lost 2 electrons. So now we're not doing a configuration of 10 electrons, we're doing a configuration of 10 electrons. Oh, it's the same as neon again. We would have the same configuration as we did right above it with nitrogen. Nitrogen has got has gained 3 valence electrons, having it 10. Magnesium, to be the +2 cation, has lost 2, making 10 electrons. So you might have particles that have the same number of electrons based on how much they've lost or gained to become an ion. So any ion that has a total of 10 electrons will have the configuration of neon. Okay? All right. Let's go and do manganese. Manganese normally has got 25 electrons as an atom, but if it's +2, what has happened? All right, it's lost 2 electrons. Okay, so let's do the configuration then of this one. Now this one we have to be very careful on. What I tell students is do the electron configuration normally. Any element that has lost electrons, I tell students to do the electron configuration of its atom state first. So let's go ahead and do manganese as an atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. This is the mistake. If you were to do the electron configuration of 23 electrons, you would do the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. You would simply subtract 2 electrons from the 3d5. Do not fall into that trap. That is not what happens. When atoms lose electrons, they always lose from the highest energy level first. 3d orbital is in the third floor. The 4s is in the fourth floor. So whenever we lose electrons in any element in the d block, we actually pull electrons from the 4s first. And you'll notice the 4s has got 2 electrons in it. We're losing 2 electrons. What we do is we literally lose the full 4s2 electron orbital. So the manganese plus 2 ion configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 3d5. So for any element in the D block, which is a very common thing on the national exam, what I tell students to do, if it's a cation, do the configuration of the atom, and then when we lose electrons, the first electrons we lose are from the 4s, and then if we further lose any more electrons, then we start pulling from the 3d. All right, so let's go ahead and do iron 2 and iron 3. I'll do that up above. Go ahead and if you need to, pause the lecture now, try to do it on your own, and then see what you get. Again, because it's a cation, I recommend doing the atom first. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. If it's the plus 2 iron, it has done what? Lost 2 electrons. Where are we going to pull the electrons from first? 3d or 4s? Correct. We always pull from the highest floor first. So the plus 2 iron ion, we literally are going to lose the 4s2 orbital. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. That is the electron configuration for iron. So any cation, do the configuration of the atom first, and then lose electrons from the outermost electron next. All right, so what happens with the iron plus 3 ion? We're going to have to lose 1 more electron. Which orbital do we pull from first? 3s, 3p, or 3d? Since they're all on the third floor, now we're going to subtract, working our way outer in. We pull from 3d before 3p. We pull from 3p before 3s. Since we have to pull 1 more electron, we now will start pulling from 3d. So we get 2p6, 3s2, 3p6, 3d5. This is why elements in the D block tend to have more than one oxidation or charge state, because they can pull from multiple orbitals. They'll pull from both the s orbital, and then they'll start pulling from the d orbital. And that's why iron can have multiple charge states. Okay? So with cations, make sure you do the configuration of the atom first, and then subtract or cross off orbitals, going from highest number first and then working our way in. If it's a negative ion, typically then all we got to do is fill whatever orbital is not filled, add enough electrons to fill it, and then you've got the electron configuration for it. Lastly, noble gas configuration. In a noble gas configuration, let's look up magnesium. In a noble gas configuration, what we are doing is looking at just the outermost valence electrons. And if you remember, to do a noble gas configuration, the outermost floor, the third floor, these are the electrons on the outermost floor. And what do we call those electrons? The valence electrons. The valence electrons are the ones that are involved in chemical bonding. And those are the most important electrons. Because they typically don't have full shells, these are electrons that are either lost or gained, and those are the electrons that are most important for us to signify. So when we do an NGC, all of the other electrons, which are found on the inner shells, these are called the inner shell electrons, we're not so worried about them because atoms do not pull from the inner shells. And because of that, these electrons really are not all that important. So doing that, we can do what's called NGC. So if you remember back in honors chemistry, which noble gas has got 10 electrons? 2, 4, 10 electrons. Neon. So what we do is we put neon in brackets, and that signifies all of the electrons on the inner shell. And then after neon, we just simply put the valence electron row, which is the 3s row, to do the configuration. So the noble gas configuration of magnesium is neon 3s2. If they just simply say what is the valence electron configuration of magnesium, all you would have to do is say 3s2. Okay. Now, one way of remembering that, look at your periodic table, is magnesium is right here. I, for you, on the national exam, would put all my numbers down here. Magnesium is on the third period, and this is the s orbital. So magnesium, the valence electrons, we always start with an s. 3s. If it's down here, it'd be 7f. If it's here, it'd be 5s. 3s, and it's in the second row, 3s2. It's another way of getting the outermost configuration to being where we'd put electrons. If we go over here to an element further on, let's say it's phosphorus. Phosphorus is right here. It's on group 15. The valence electron configuration for phosphorus, it's on the third floor. The first orbital we fill on the third floor is the 3s, and over here is the 3p. And if you count 1, 2, 3, 4, 5, there's 2 electrons in the 3s and 3 electrons in the 3p. We have added 1 electron in each of the vertical rows, and now it's 3s2, 3p3. Again, the valence electrons, if we add them up, have 5 electrons. Phosphorus is in group 15. If you remember from honors chemistry, if it's in group 15, it should have 5 valence electrons, which is signified by 3s2, 3p3. It's got 5 electrons, 2 in the s, 3 in the p. That adds up to its valence electron number. So most of you probably with noble gas configuration want to write out the whole configuration and then identify the largest number out in front. Okay, draw a line that divides that, figure out how many electrons are on the inner shell, which noble gas is that, and then everything after that you'd write down, and that'd be the noble gas configuration. So go ahead, go to the homework, which is the next page, page 5. Identify how many electrons it is. Is it an atom or is it an ion? Do the configuration of it, and I've put the homework answers on Canvas. Go ahead and give them a try and see how you do. If you have any questions, please give me an email or give me a Canvas notification. Thanks again for listening.